Okay. And homework 6 I expect will be on, this will be October 5, right? Midterm 2, do you guys know what it is? And there are only 2 midterms in this. Sometimes there are, I keep 3 midterms, so there will be 2 midterms.
Last year there were 3.
Yeah, and that was primarily because it was an online. So and that was a first full online session. So I was not sure how it's going to go because it was going to be take-home exams completely. So I made it 3 so that I can drop 1 if necessary, if something goes wrong. But it went smoothly. It was different points. It was more of a backup. So, but again, if you guys think that there should be more than 1, but you guys have to talk to everyone and let me know. If it is just to boost your grades, don't worry too much about that. I mean, even with the single midterm remaining and the final exam, you don't lose too much at this point. Just keep working hard and don't give up. That's the main thing. There's a lot of curving I do, and I will come up with a curve. On Friday, I will give you the actual grade that you have, because I do a curve of like if you have submitted the quiz, I return back some question, some points based on that. So I'll give you the actual standing on Friday. I would have liked to do it today, but I didn't finish the grading of the homework yet. I started it and then I noticed it's the same mistakes you're doing in the exam, and I was a little upset about that too with myself. Okay.
In this second midterm, you would make question from the first one, including first midterm.
Officially, yes. Like the way I answer typically is that yes, because all the concepts are carried on. But having said that, probably, I mean, I can, but I usually don't expect me to. Like mostly it is the question between midterm 1 and midterm 2. Unless, for example, I see that index notation I feel is used a lot. And then I see that many of you guys messed up in the index notation. So that I might, but I will tell you guys that, okay, I might do that again. So yes, to answer your question, officially yes, but probably practically no. But the final exam will be cumulative. Okay. Again, when I do that, it's about 70% new material, 30% cumulative. Is that clear? Yeah. Okay. So we introduced the idea of analytic function. So analytic function is if you have a function, complex function f. In principle, this depends on 2 variables, right? There is a, let me actually say, so first there is a complex number, right? So there is a complex plane, which is x plus iy. I is square root of -1. In many ways, these are 2 real variables, x and y, and a complex function f of f in general can be equal to, let's say, it can depend on u of x comma y plus I times v of x. That's a general way you can represent a complex function. So this will be f of z, but in this way of writing it, what we notice is that there is two variables x and y, and that's of course can be represented by z, but two variables being represented by a single complex number is probably a constraint already. One in general can construct a function of the kind f of, or let me say, since it is two variables x and y, I can write u prime as a function of z comma z star. So what I mean by that is, or let me put it this way. So this is your complex function, correct? And we have Cauchy-Riemann condition. I'll bring that in a few minutes. But let us consider a transformation where z is equal to x plus iy and z star is equal to x minus iy. I can invert this. That means x is equal to, if I add these two quantities, it is z plus z star divided by 2. So it's correct, z plus z star, z plus z star divided by 2, and y would be equal to z minus z star divided by 2i. Z minus z star divided by 2i. If I were to replace this z and x with z and z star, z minus z star, that means this function can be written as a new function and u prime, some it is since I'm representing in terms of z and z prime. So this is a new function which is written in terms of z and z star plus I of or I times b of z star. Is that clear? So it's not just xy dependent. Sometimes you can, I mean, it's a transformation. I can transform it into any variables, any two variables, and if z z star. But we said that we would like to have a complex function whose derivative is well defined. So if so, analytic function is when so if derivative of f with respect to z has to be well defined, has to be unambiguous, then f needs to satisfy the Cauchy-Riemann conditions. Which are basically that derivative of u with respect to x has to be equal to derivative. So the way, so this is dv by dy, and derivative of u with respect to y is equal to also derivative of with respect to x. And since x and y are two variables, it's usually hard to imagine what this constraint represents. So whenever this is there, there is a unique derivative of f with respect to z. But we would like to know, okay, that's good, but how does this look like in terms of z and z star? These conditions, how does it look like in terms of Z and Z star. Let us see, and that will give us some insight into this. So change this. So whenever we want to change X to Y, we would like to do this. So d by dx is equal to, use a chain rule now, that is Z and Z star. So this is dz by dx. Z plus star over dx star. It's double, right? And that's equal to the derivative of Z with respect to X is 1 using this equation. The derivative of Z with respect to X is 1. So that's simply d by dz itself plus dz star with respect to X is again 1. So this is plus d by dz star. Z star. Is that clear? Like I take the derivative Z with respect to X and do the same thing with d by dy. That's equal to dz by y. And Z with y is 1 over I. The other one is minus 1 over I. So it is 1 over I. So noticing that u now is, so u of xy is the same as u prime of c comma z star, and v of xy is the same as v prime of z comma z star. So let's put these conditions in terms of z and z star. So we learned that du by dx is the same as du by dz plus du by dz star u prime. And du by dy is the same as du prime by dz 1 over I minus 1 over I prime star, and dv by dx is the same as d prime over dz plus d prime over dz star. And dv by dy is equal to dv prime 1 over. Right. And I'm not seeing this. Okay, I'm a little confused. So we would like our Cauchy-Riemann conditions in terms of Z and Z star. So we would say that our conditions are Cauchy-Riemann conditions are du prime over dz plus du prime over dz star equal to 1 over I times dv prime over dz minus 1 over I prime over sure. And similarly, so this is du prime and minus no, this is plus the other one is minus. C I minus 1. But that's not what I want. Oh no, I think okay. Correct. But I would like to write these things in terms of u, in terms of f instead of u. So this is good. So this is the new conditions we have found, Cauchy-Riemann conditions in z and z prime. But still, it is not very insightful. Let's write in terms of f. Right? So f was equal to u of xy plus I times v of xy, but now we're writing in terms of z. So this is u prime of z comma v star plus I times v prime of z comma z star. So let's try to write this in terms of u prime and v prime, basically combine this in the right manner. So let's add these two equations first. Let's multiply this with an I and then add this together. And right, because I will get du prime plus I dv prime there. So then I can collect it as a f. So let's do that if I can see that. Huh? Correct.
1 by I minus 1 by I.
Oh, is that a mistake?
No. I'm confused with it.
Oh, why is this? Okay, so because I said this has to be equal to this, right?
Yeah.
Because du by dx is dv by dy. So this is equal to this. So I wrote this down here, and that's down here.
Okay.
Right?
Yeah.
And
There
then,
has to be a minus.
Then after
oh, that has to be minus. I see. Yeah, this is equal to this. So yes, you're correct. This whole thing will be a minus. Correct. Very good. Thank you. Thank you. So let's multiply by an I in this equation and then add these two equations. Okay. So that gives us, you have, suppose we add them du prime by dz. When I multiply by an I and then add them, these two cancel out. These two add up. So it is 2 times that. Right. After I multiply by an I, these two add up. These two cancel out. After I multiply by an I, so after I multiply by an I, so it is 1 over I, so it's 2 over I. That's equal to 2 over I dv prime over dz, and this is minus 1, and there is an I, and I put it down so it becomes plus, these cancel. So that's what you get. Put this upstairs. This implies that dy by dz of u prime the minus, so it becomes plus I times u prime is equal to really? Something wrong. No, this is df by dz. Right. And that's equal to 0, right? Is this right? That's it. So multiply by I that's 1 over I. Go to the left. Minus of plus I v prime. Right? Okay, let's do this one. What if I subtract them? I do a 1 over I here. And okay. Oh. So multiply by 1 I and then subtract out. So I'm going to multiply by 1 over I. So multiply by 1 over I here overall, and then subtract out. Right. So that cancels out. This now, when I subtract, adds up, right? It's 2 over I dv prime over dv star. Something messing up. So that's here. So that's 1 over I, that becomes a minus, and minus that cancels out. 1 over I, that's minus plus dv prime, and it's plus, that is 2. And that's the same as d by dz star. D by dz star. I put an I there, bring it down here, so it is u prime minus I prime equal to 0, which says that this is f and this is z star. So this is d by dz star f star 0, which also means that z is equal to 0. Except that that's not what I want. I want z star. So we made a mistake here. Yeah, what's the mistake?
We multiplied here by I for addition. 2 by I. How that 2 by I can be?
Which 2 by?
That 2 by I.
Oh, 2 by I. So okay. So the first thing. Yeah. Okay. Let's see. So what I did was I multiplied by I. Right, all through this. So when I multiply by I cancels out, they add up. So it's 2u prime.
This cancels out.
And the same thing here. So there is a minus I, which is basically 1 over I. Right. So that cancels out, right? And I add.
Minus.
Yeah, sorry, adds up, right? 2 over I v prime over c. Isn't that correct? and these cancel out.
Yes.
Agreed? Did I do this right? Z is x plus I, right? Z star is x minus I, right? Right? Like what I expect here is that instead of this, it should be F with respect to Z star. That's what I expected. So the Cauchy-Riemann condition just means that it is independent of Z star. So I think I made a mistake. Constructionist, I suppose. Oh, this is dz by dy, right? Dz by dy is I, right? I wrote it as 1 over.
Wow.
Dz by dy is I, right?
dg by yeah, I
Right. This derivative of z with respect to y is I.
multiple.
And derivative of z star with respect to y is minus I. I don't know why I wrote 1 over I. Okay. Okay, so my bad, sorry. Okay, so this is okay. So back camera also has to go back. Okay. So this should be I. Right. And this should be minus. Right. So very clear. Okay. Sorry about that. And that changes this all to this becomes I. It's minus I. So it becomes okay. So this becomes all right. And this one is 5. Yeah. Okay, now let's again try. Okay, so yeah, I again multiply by I again. Simply I. If I multiply by I, this cancels out, right? I square is -1, that cancels out. All right. So let me rewrite this now. So U prime cancels out. I square is -1, so it is 2 times U prime over dz star. Right. And this is equal to the minus I. When I subtract it out, it adds up. So it's 2 times I times prime over dz star. That comes up, and this cancels out. Minus I and minus I cancels out. So this is equal to, this implies that d by dz star of prime minus I equal to 0. That implies that derivative of f star with respect to dz star 0 takes a complex conjugate d by z. What is it? Did I again get the same thing?
No, please, okay.
No, this is minus, right? Now this is minus, correct? So minus, and I'm adding, so it is plus. This is minus, right? Correct. Minus I and minus I adding.
Minus 2.
You are adding.
Adding, right? Because that's why this cancelled out. I square was minus 1. Correct.
Mm.
Yeah, I also thought I was subtracting. So then when I take it to the other side, this becomes plus. So this is not correct. So this is d by dz star f. Okay, after some mistakes. Okay, good. Okay, let's do the same thing now. So now we want to keep the u, right? There are two equations, so there should be one more equation in here. And for that, we subtract, right? Or multiply by I this time, and again add, right? If I add again this time, this cancels out. So it is 2 times I u prime over dz. This cancels out. I'm multiplying by I, so that's minus 2 prime over dz. And this again cancels out, so it's plus, and the minus that cancels out. And this time I put in the here, so this is equal to this again I times u by dz of u prime so that's 95. This is the plus d prime, and it goes on the right hand side, becomes a minus, which is the same as d by f star with respect to dz is equal to 0. Take a complex conjugate of this. This means that f by dz star is equal to 0. Right. So Cauchy-Riemann conditions are the same. Now there's a very simple relation of Cauchy-Riemann conditions that for Cauchy-Riemann conditions in this new is if you have a complex function f, which is in general, you can construct, if you want to construct functions out of complex numbers z, then you can construct it out of z and z star. Then you just have to check that partial derivative with respect to z star is equal to 0. That means no z star dependence. If a derivative of a function with respect to a variable is 0, that means there is no dependence.
Yeah.
Correct. no Z star dependence. So what is the definition of an analytic function? An analytic function is, usually we think of it in terms of X and Y. It satisfies Cauchy-Riemann conditions in this way, or a simpler way to see it is that think of it as Z's. There should be no Z star dependence at all. So let's do an example. So let's say F is equal to Z times Z star. That's the magnitude of Z star square. And now suppose I ask you, is this analytic or not analytic? What would you say?
Magnitude, right?
Yeah, magnitude of Z square means that it is Z times Z star. Correct?
Yeah.
So now tell me, is this analytic or not? So if it is analytic, it has to satisfy this.
It's not.
It is not, right? Because there is a Z star. When I take the derivative of the derivative of F with respect to Z star is equal to Z, which is not equal to 0. It's not analytic. So that's an algebraic way of saying it, but let's check. We also know that it has to satisfy this conditions, correct? So let's, so Z star is nothing but X square plus Y square plus I times 0, right? So U is equal to X square plus Y square and V is equal to 0. Correct? If I were to write it in terms of U and V. So what is du by dx? It is 2 times x. What is du by dy? It is 2 times y. What is dv by dx? That's 0 because there is no function v at all. And dv by dy is equal to 0. So this is not equal to minus of this. This is not equal to this. So this is not analytic, right? Not analytic. So let's do another example where it is analytic. Any questions at this stage? Clear? Yeah, this should have been straightforward, but I think I messed up. Okay. Okay, another example. If F is equal to Z square. Okay. What is it analytic?
It's not again. Most probably.
No, it's Z square one, yes.
What is
It's
derivative with Z star?
2Z.
0, 0.
0.
Yeah, yeah.
So it's satisfied. Correct. So most probably it's analytic. Correct.
There is
So,
nothing.
so derivative of F with respect to Z star is 0. So probably it's analytic. So if there is a confusion, let's write it in the XY terms, right? So this is equal to X plus IY whole square. Right? So this is the same as X square minus Y square and plus 2 times I times XY. So that tells me that u is equal to x squared minus y squared, and v is equal to 2 times xy. So what is derivative of u with respect to x? It's 2 times x. Derivative of u with respect to y, 2 times y. V with respect to x. So this minus, right?
2.
Minus. Okay. Minus 2y. By dx, that's 2y. d by dy. And clearly, we see that these two are the same. Right? That's one of the Cauchy-Riemann condition. And this is negative, right?
Yeah, it is
So- and that's indeed true.
analytic.
So it is analytic. Let's do a slightly more involved example, just for the sake of describing it. So let's say exponential of x, right, or exponential of z. So let's say f is equal to exponential of z. Is it analytic or not analytic?
Most probably not analytic.
Why most probably? There is no z star in here, right?
Okay.
So derivative of z star is 0.
Zero.
Right? So it's not analytic immediately. You can say that, but let's do it using x and y functions. Okay, we don't have to do that. This is sufficient, right? Sufficient condition, but we will also see some continuity equations that spoils this. But as far as Cauchy-Riemann conditions are that it doesn't satisfy, it's not analytic immediately. Okay, but it's good to see this, how this goes through in the xy space also. So this is equal to e raised to x plus e raised to y, so it's e raised to x plus e raised to iy, right? Probably that's not the best way of saying. So probably this is x plus iy. No, it's okay. E raised to x and then e raised to iy. Right? That's the same as expand this as cosine and sine. So this is cosine of y plus I times e raised to x sine of y. Right? I expanded e raised to iy in that form. And then we have u is equal to e raised to x times cosine of y. And b is equal to e raised to x sine of y. Du by dx is exponential itself. It's cosine of y. Du by 5 is minus y. dv by x is exponential of x sine of y. And dv by dy is equal to e raised to x sine of y. And again, we see that this is actually satisfied, and this is also satisfied. Dotted line means that it's a negative of that's what I mean by that. So that works. I have mentioned this before that analytic function requires that the Cauchy-Riemann conditions should be satisfied.
Mhm.
But the opposite is not true. If the Cauchy-Riemann conditions are satisfied, it doesn't mean that it is analytic or everywhere on the plane. Sometimes, somewhere it will be off. And let's do some examples on that. So, but before that, let me clarify.
Another
Yes.
thing, here there is no Z prime dependency is equal to Z, so it should be 0, you told.
Correct.
But right now it's following the Cauchy-Riemann conditions of d by d.
Yeah, that's correct, right? So this is 0.
Mhm.
That means it is analytic. That implies it is analytic. Right?
Mhm.
If it is Z star independent, it is analytic.
Yeah.
Right? It is not that it is, okay. So again, I say, if it is analytic, it has to satisfy the Cauchy-Riemann conditions. If the Cauchy-Riemann conditions are satisfied, it doesn't mean that always it is analytic. But Cauchy-Riemann condition has to be satisfied. If it is 0, if it is not 0, then it is not analytic. Is that clear? So maybe the way to say it is that, so F could be analytic. If derivative of F with Z star is not equal to 0, F is not analytic. Then there is no question. But here you cannot proceed further. Is that clear?
Yeah.
Right. Okay, so that is one. This is all algebraic, right? At this point, we are doing, if you want to check if it is analytic or not, we immediately see that, oh, algebraically, that's the Cauchy-Riemann condition. So it is good to have a geometric picture also. So this is called, I'll say, isotropic derivative. What do we mean by that? So isotropic derivative means that, let us say there is a Z plane. This is Z plane. Since a complex function is two-dimensional, I cannot draw the third dimension here, right? I have to actually go to another plane here to draw the complex function. This is the function f of Z, which is basically, this is U and this is V. This is X, this is U and this is that clear? So if I want to map a function for every point here, there is a complex function there, right? So this point might be somewhere here. So that's one point gets mapped to that. Very close to that point is somewhere here. That might get mapped to here. That's point 2. There's another point 3 here. That might get mapped here. Is that clear what I mean? Like I'm taking a point here. There is a complex function there. That's this point. Right? Adjacent to that, there is another point in there. Okay. Now notice that how do we think of derivative? If it was a one-dimensional, I can come from the left or from the right, and the derivative has to be the same. Here, I can come in various directions. Like from 1, I can go in the direction of 2, or I can go in the direction of 3, or I can go in any direction. It will be any infinite number of directions I can go around 1, and there will be similarly an infinite direction of points f plus dz. So this, if this was z, this is f of z, and this is f of z plus dz. And anywhere I go, it has to be the same. Isotropic derivative means that it doesn't matter in which direction I go, derivative will always be the same. Okay, so that's a very big constraint. That's not the case in 2 dimensions in vectors. It's only on a complex plane, whether I go here, 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 wherever I go, it will correspondingly go somewhere. But if you subtract and you take the difference in the z, it will all become the same derivative. So let's check this. Okay, so we take a simple example and let's check that. So example again. And let's say f is equal to z squared. And remember, this is x plus iy. Oh, let's just say z squared. Let's make our delta z. So remember, df by dz is equal to limit delta z going to 0 of f of z plus delta z minus of f of z divided by delta z plus delta z minus z. So let's say let my delta z be equal to delta x plus I0. What does that mean? To have a picture of that. So go ahead.
There is no imaginary part.
There is no imaginary part. So which means to say that if this was my z, I am moving in this direction. That's my delta z. I could remember I can move in any direction. I'll first move in this direction, get my derivative, and I can take any other movement, but I'll take it in the y direction next. Right? First, let me say just x direction, and let's see what happens. So derivative df by dz is equal to limit. Now delta x, right? Delta z is the same as delta x. Now delta x tends to 0. That means I'm on the x-axis. So I'm going from a point z to along the z direction. F of z plus delta z. Z plus delta z is here, right? Z squared. So it is z plus delta x squared. Is that clear? So f of z plus delta z, and this is minus f of z itself, so that's z squared, and divided by delta z, which is delta x. That's equal to limit delta x tends to 0. Z square cancels out, and there is a 2 times z times delta x plus delta x squared divided by delta x. That's the same as g times z. So limit delta x tends to 0. 2 times z plus delta x. In the limit delta x tends to 0, the first term survives, the second term goes to 0. So the derivative is actually 2 times z. So if I go make a small tiny change along the x direction, I get the derivative to be 2z. So now we will see what if I go in some other direction. As another example, I'll go in the y direction and see what happens. Like one might think that there is an I here, but all this will always compensate and give you It's the same thing. So let's see. Okay, so this time let delta z be equal to, I'm going in the y direction, so it is 0 plus I delta y. Right? That's my displacement in the y direction. Right? In general, like for example, I can ask in the exam, a simple thing to ask will be, what if it is delta x plus I delta y? Right, some 45 degrees. If I go in the 45-degree direction, what will it be? Something like that. Okay. So df by z then is equal to limit delta y, this time going to 0, to I delta y, but I doesn't matter, right? So it is z plus I delta y whole square minus of z square divided by I times delta y. So that's equal to z square cancels out. Again, that is limit delta y comes to 0 of 2 times I times z times delta y minus delta y square divided by I times delta y. And again, this is limit delta y 0 of 2 times z. One of the delta y's cancel out, so it is plus I times delta y. Exactly equal to 2 times z. Any questions? Okay. Let's have a quiz here. So for example, so extra credit, right? So that's it. So quiz. Go in the, so we'll start from z, some arbitrary z, and go in the 45-degree direction. Right? Yeah, 45-degree direction. Right? So let's say this is how you go. Right? And let's the length of that be delta s. Right? So delta z now would be equal to, we are going 45 degrees, so it is 1 over root 2 plus I times 1 over root 2 times, so since we are going in this line, it could be anything, that's delta s, that's the length you go in that. So you have to take the limit, this goes to 0. But that's your 1 over root 2. Okay, and you have to show, find f by dz. Okay, the picture clear?
Yeah.
Okay. So that's all, gives a reasonable picture of what if it is analytic. Okay, that's isotropic. But what if it is not analytic? Like, does this mean that this will not work? How does it not work? Right? So it's good to check that. So let's do an example where it is not analytic and see what happens. So let's do an example of f is equal to z star. Is this analytic?
Yeah. Because if I divide it by that star, then there is non-zero value.
Yeah, so is it analytic or not analytic?
It is not, no,
Analytic.
Hmm?
It's analytic.
It's not analytic.
It is not analytic, right? Because z star, derivative of z star is not zero.
Yeah.
So it's not analytic, right? Immediate. So it's not a good function as far as we are concerned.
Yeah.
Like if the derivative doesn't exist, it's usually not very useful. Okay. But let's see what this is. So let's first go. Let delta z be equal to delta x. And do the same thing. And derivative of the f by z equal to limit delta x tends to 0 of z star, right? So if so this is z is x. So this is z star, that's your function. So I should do this also, right? That is the dz star. It's dz star. So this is z plus delta x times z plus delta x star. Agree? Z plus delta z, f of z plus delta z, right? Wherever there's a z, I have to put in a delta z, but delta z is delta x. Minus of z star. Divided by delta x. So I will do this. That's equal to limit delta x tends to 0 of z star cancels out. That is a z times delta x star is the same as delta x, right? X is real. So it is z times delta x plus delta x times z star. And then that is delta x squared. So that's equal to delta x cancels out. So that's the limit. X comes to 0 of delta x goes away. So it is z plus z star plus delta x. So that's equal to delta x is 0, so that's z plus z star. And that's equal to z plus z star 2 times x. So that's your derivative. If you go in this direction, go along the x direction. Okay? So there is an arbitrary z there. If you go in this direction, that's your derivative. Now let's go in the y direction and see if it is the same or not.
Yeah.
So it was 4 minutes remaining. So let's this time let's say let delta z be equal to 0 plus I times delta y. Again, the idea is that you have this as z and you go in this direction. Delta z. So the f by z, derivative of complex function, limit the y tends to 0, and now z plus I delta y times z plus I delta y star minus z star divided by I. So that's equal limit 0. Z star cancels out, so that is a z times minus so minus I delta y z, that is a plus I delta y z star, and there is a plus delta y squared divided by y. So I didn't mess up.
Where is the I?
Where is the I?
I delta y.
Oh, I delta y. Thank you. Yeah. So cancel out here i's or delta y's, so that we have the I delta y is gone, so it is minus z plus z star, and that is minus I delta y. That's the same as, oops. That's the same as minus z plus z star. This time, this is clear that this is minus 2I y, right? Which is not the same as the other one, correct? It depends on where you are. So x, so if you're on the 45 degrees axis, it is the same because x and y is not the same, but still that I is there, right? So it won't be the same even there. So it's not the same. So it's not that the derivative doesn't exist, it's not the same when you come from different directions. Right, that's the feature. And again, you can have a quiz. Do the same exercise for here, right? So when delta z, do the same thing for 45 degree line, right? Check if it's the same. What will that be? Oh, pretty much exact. Any questions?
If as far as the definition of derivative, it has to have derivative from left hand side limit and right hand side.
Right hand. That's a one dimension. So if it was one dimension, left and right has to be the same. Otherwise, you don't know whether it's the left one, it's the right one. Now we are saying derivative from all directions has to be the same. That's just the definition of analytic function. In two dimensions, that's not the case. If it was not a complex function and we are doing two dimensions, you will have a gradient in this direction, gradient in that direction. That is a directional derivative. But that's okay. But if you require it to be zero, then it's a more fundamental, or it's a very constrained function. In electrodynamics, this is equivalent to, we do say somewhere there that cross of an electric field, sorry, the curl of an electric field is zero. If you're doing two dimensions and the curl of the electric field is zero, that's equivalent to putting the condition that it's an analytic function. In two dimensions, notate electrodynamics is done in three dimensions. If it is two dimensions, and if you say that the curl of the electric field is zero, that's equivalent to saying that that's an analytic function. The electric field then is very constrained and it will have all these properties. So that's one way of imagining that, or having a physical picture. Good.